Carvalho. I'm a senior software engineer here at Sky, and I'm here to talk to you about combining refinement types with type class derivation, which is something we use quite a lot in the project I'm currently working on. So for this talk, I'm going to go over some ways to make illegal states unrepresentable without any additional libraries, and then I'll go into introduce refined as a library, and then I'll go into type class derivation. The whole time, there's all of the code examples are based around a simple type class that I defined, just a JSON decoder type class, and you're going to see the evolution of it, and hopefully at the end you'll understand why this stuff needs to be used everywhere. Cool, so the motivation for this talk. The project I'm working on is called MAP, and it's a data ingestion pipeline. And primarily we need to serve correctness to our clients, and resiliency and reliability, but mainly this talk is about how we express correctness at the same time not increasing the maintenance burden. So most of what we do in this, probably I would say in the industry as a whole, is we need to deserialize and validate some data from somewhere. And the main, like I say, the main goal behind this is we want correctness, making illegal states unrepresentable, and the biggest challenge really is boilerplate. Like as our systems grow and we have to handle more data structures and the data structures we already support evolve, we don't really want our maintenance burden to increase. We want to be spending our time writing code for more interesting things, not deserializing JSON, for example. So here's pretty simplified version of some of the domain at Sky. So we have a movie. So a movie has an ID, it has a string, title string, has a list of credits, because if there wasn't any credits, then no one would be working on the movie, so there wouldn't be a movie. There's a production year, some list of supported languages, an image URL, and as you can see here, credit has a first name, last name, and a role. So some of the constraints we may want to put on this data for our validation, we may want the string ID to be a UID, the title string to not be empty, the list of credits to not be empty, because as I say, no one's working on it, there's no movie. Production year greater than or equal to 1889. 1889 was apparently when the first movie was made, Wikipedia. Image URL string. It's not really a URL unless it adheres to the URL format. Credit, first name, last name cannot be empty because people have names. And a role, so something from some predefined set of values. And also language is a pretty interesting one. So we say to our clients, when we surface a language, it's in this format, ISO 6392. So ideally, this needs to adhere to that format. So our clients have a common format for languages. So a couple of ways without any other libraries to make illegal states unrepresentable at the class level. So one example is using assert require. So I guess most of us know we don't really want to do that because it's unsafe, so it's going to throw an exception at runtime. Another option is smart constructors. This is a weird one. Maybe someone is going to talk to me after this and explain to me that there's a better way of doing this. But Scala gives you the ability to make constructors private. But if you use it in a case class, then the apply method is still public. So here, to get around that, we're redefining both apply and copy, and making them safe in the fact that they're going to return, like here I put an either of invalid or movie. So you'd have your validation logic within that apply method. And you can probably tell that there's a lot of boilerplate even just there, but as you need to support more structures, that is just going to keep happening and happening and happening. You don't really want to do that. So here, so I mentioned earlier a simple JSON decoder type class. So imagine just a type class with a single method, takes some JSON and returns either some error or the type that you want to decode into. So this is what some of the type class instances may look like for that type class. So here we've got like a string decoder, just make sure that there's a JSON string and then returns a right if it is. Int decoder, a list decoder, and a UID decoder, which is composed of the string decoder and making it using Java util U. Next, I've got like some, again, manually decoding JSON, but here I'm providing the type class instances for the overall case classes themselves. So I've got an instance here for a movie, getting fields from a JSON by a key. So I want to try and decode the ID. That would implicitly, that's going to call the string decoder. Same with title, list of credits, etc., etc. But you can see that. So here I've got these defined for a few case classes. Again, as your system grows and you need to handle more, you're going to have to keep defining these again and again and again. And like I say, it's not really interesting code that you want to have to spend much time writing. This role one at the end is a bit more interesting because the role is a co-product, so it can be one of a number of things. Here, I've just defined it as either an actor or a writer. So as it's a co-product, it can only be one of these things. So I'm trying to decode an actor. If that fails, I'm going to try and decode it as a writer. So I want to talk to you about refine. So these aren't ideal. This is where it gets incredibly ideal. So refine is a Scala library for adding predicates to types. Support of a library from Haskell called refine as well. But with refine, like a lot of the types in the case classes that I've shown you are strings. Very rarely do you want any string. Like most of the time you don't want it to be empty. It needs to have some more meaning other than just string. And that's where refine comes in. So a refinement type is a base type plus a predicate. So here I've got a non-empty string defined, which is string refine non-empty. And this means that you cannot have an instance of this type that doesn't adhere to that predicate. So you know at a type level, when you have one of these, you know for a fact it is a non-empty string. Same below with positive integer, int refine positive, and the one below int refine greater. Now I've used positive int and more than 10 for a reason, because refine also has some inference. So refine knows that an integer with this predicate, int refine greater than 10, has to be positive. So if you've got something that accepts a positive int, you can give it this. Also, so refined, there's something really powerful in refined. When if you just add this import here, you'll get a compilation error if something that you try to instantiate doesn't adhere to that predicate. So those 3 lines there just wouldn't compile because trying to create a non-empty string that's empty, negative integer for something that's positive, etc., etc. But generally we have to deal with runtime. So a lot of what we do in our project, like I say, is deserializing some data from some input. We don't know what that data is until runtime. So refine gives you this refine v method. You give it the refine type that you want to refine it to, and then you give it your value. So that will return either a string, which will contain an error message, or an instance of that refine type. So here, I mentioned earlier the constraint that we may want to add to languages. So I mentioned ISO 6392. Here I'm just trying to demonstrate the granularity that you can achieve with refined. So here I'm defining a predicate on a string which has to match this regex, and this regex is what the ISO 6392 adheres to. So it's like 3 characters, potentially a slash with another 3 characters. But that's the kind of data validation you can express at a type level, which for me is insane. Then here I've enriched, I've updated this movie class that I defined at the start. So ID is now a UID. The title is a non-empty string using refined. Credits is a non-empty list. This isn't using refined, it's using a catch data type, but it's the same sort of thing that I'm trying to convey. Production year. So again, the level of granularity that you can go to. So the production year, the integer must be greater than 1889, otherwise it wasn't created. Languages here using that type alias defined above. And image URL, so refined comes with this URL predicate already, so you can express that a string has to adhere to the URL format. And at the bottom here, I'll have the refined type class instance for my simple JSON decoder type class. And that is how easy it is. And if you go to the refined GitHub repository, you can see loads of integrations with other libraries, and they're generally, it's just a package object with like however many type class instances for however many type classes they have. But that's how easy it is. You just provide it an instance for T for your type class, validate and ref type. These two refined handles for you, so you don't have to. You just add it to the signature of your method, and refined is what handles creating those instances. And here I'm just calling my JSON decoder and then refining that type. And this type class instance for refined works for any refinement. That's how easy it is. So it's so easy to add support, refinement support to your type class. So now that I've defined that, we still have the problem of boilerplate, which I showed you earlier, where we have to define a type class instance for all of our case classes. So here I'm going to talk about shapeless type class derivation, because that's generally the most popular implementation of it, and how we can use it to remove our boilerplate. So there's a few important concepts in shapeless. Heterogeneous lists, or H lists. This is a list that can hold any type, but at the same time it's type safe. So the compiler knows, for one, the compiler knows how many elements are in your H list, but it also knows the type of each element in your H list. There's also co-products. So co-products take the form of something like an either or a seal shape family. And then there's generic. So generic is a type class from shapeless, and this is incredibly powerful. And this type class allows you to convert to and from any product or co-product into a shapeless generic encoding of that. So the shapeless generic encoding of a product type, like this movie, is an H list, and you can see generic movie defined below, the type AS. And with a co-product, so shapeless's generic encoding of a co-product is a shapeless co-product. And so an H list always ends in H0. H0 represents an empty H list, and C0 co-product definition always ending in C0, as you can see at the bottom. Cool. So how do we use shapeless to derive type class instances for products? You have to define a type class instance of your type class for an H list. Oh, I've got email. Cool. For an H list. So the definition of this, you can see here, you provide the instance for the current head of that H list, and then plus the instance for the rest of that H list. So what shapeless will do is it will use the type class instance for your head type. And here you can see that we're running that type class instance here. And then below you can see we're referencing T decoder, which is the type class instance for H list type. So then it's just recursive. So then it's a recursive call, right? So it's going to recursively resolve your type class instances until it builds. You can see the return type of this JSON decoder here is HT, and that's an H list definition. So it's going to recursively derive your type class instances until it's built. It's built the full H list for what represents your product type. So the instance at the bottom, I'll talk about the H1 in a minute, but the instance at the bottom is what actually applies this H list instance. So here at the bottom, I've got running the encoder from the head type, and then I'm calling this gen. So I've got a type class instance for generic for my type in here, and I'm calling that. So like I was saying a minute ago, so the shapeless generic type class allows you to go to and from your product type or your co-product type to the generic encoding. So once this HList one is built, the HList version of your product type, this generic decoder is able to then use that in using generic, and you can go from the HList to your product type. You always have to define an instance for HNL, which isn't really used so much. but it's generally my understanding is that h0 is what terminates the end of the h list. You can see I've got lazy here a couple of times. This is to allow the shapeless type class derivation to work with recursive types, because without that, the compiler is going to freak out and think that it's going to get into an infinite loop. So shapeless provides lazy to sort of defer that derivation until runtime. So you don't need to. So it allows recursive type. So it's generally a good idea to use it for any head type. Shapeless type class derivation for products. So see at the top here, I've defined one for CNL, and it throws an exception, which, I mean, I don't know if most of you are like me, but I hate writing the keyword throw in any Scala code. But don't worry too much, because it's CNL is comparable to nothing. You cannot have an instance of that. So it's just to get it to compile. And then below that, I've got my co-product instance for my decoder type class. It works in a similar way to the H-list in the sense of recursion, but the difference is, like a co-product, it can be one of some types, or it can be one of many types. So we're not accumulating a list or an H-list. We're just trying each head type until we get something that works. So now with those type classes in place, and removing my movie type class instance and my credit type class instance, just having those instances that I've shown you in scope, we're able, this code at the bottom will compile. I definitely sorted out that formatting earlier, but not still. No. But you can see here I've added more types as well, and I've been able to add more types without having to add any type class instances. It's able to derive that based on the types for the primitives and the refined types that I showed you earlier. So you can see here how, as your system grows, you need to handle more data structures. Your boilerplate doesn't grow with that. Cool. So I'm going to go over some existing implementations. JSON decoding with Circe. You can probably tell that my code examples were inspired by that if you've used it. Type-safe configuration, decoding with pure config, command line argument parsing with Scott, and deriving Scala check optional instances. So all of these examples are libraries that support type class derivation, but also have refined integration. So JSON decoding with Circe. This is literally all of the code. We use this pretty heavily. This is all of the code that you would need to be able to decode that JSON. So all I've done is added a couple of imports, defined my product type, expressed all of my validation at a type level. That's what's really key. I've raised pull requests in my project that to be honest, don't have tests. People may. But all I've done is just, if I needed to add some validation, I've just been able to express it at a type level. And literally that's all the pull request would be. And obviously this would work for any other product types that I may need to add. And yeah, you don't have to write any instances. It's all of the primitive, all the instances for the primitive types are defined within Circe, and it's got refined support, so it's all handled for you. Type-safe configuration decoding with pure config. Now this is, I purposely chose this example because we saw this in my project, so we use the confidence schema registry quite heavily. And you're given a Java library to use it, but when you try and create an instance of the schema registry Java client, you give it a URL, and it will throw a runtime exception if that URL doesn't have the protocol at the start, or if it isn't the URL. So this hit us quite a few times, because like you don't always expect to have to put the protocol there. So in order to guard against that, all I had to do was change the type of schema registry URL in our app config class, and just refine it with the URL predicate. And that way I know that I cannot get an instance of app config where the schema registry URL doesn't adhere to that format. And again, this is all the code that you need, pure config, other than two imports that haven't got there. But pure config handles deriving the instances for you, and it's got support for refined. So this is all you need. Cool. And that's the end of my talk. So some conclusions: use refined a lot. Most of the time, when you've got a string, you don't want anything. You rarely want anything to be in that string. To be honest, you rarely want it to be empty. But so yeah, use refined a lot. it really allows you to make the incorrect impossible, but safely. That's what's important. So type class derivation, let the compiler handle your boilerplate for you. As you evolve your current domain models, or you need to support deserialization of extra data structures, you don't have to you don't have to increase your maintenance burden in terms of code, because type class derivation is going to handle all of that for you. There's a couple of drawbacks, but I'm going to mention drawbacks, but they're drawbacks, but the benefits massively outweigh the drawbacks. So fully automatic derivation is going to create more objects at runtime, but there is a solution to that. You can use semi-automatic derivation, and this is just where you statically define your type class instance, but your type class instance is doing nothing other than calling the type class derivation mechanism. So it's generally going to be one line. It's not going to be this whole massive thing that I had defined at the start, and that will prevent extra instances of that type class being created at runtime. The other main drawback is compilation time. So it can get pretty painful, I won't lie. But a couple of things that I would suggest. The first one, don't compile from clean often. Especially when you're developing, I've seen it happen a lot where people don't leverage incremental compilation. You really should do that regardless of type class derivation or not. And if it's really becoming painful, there are other implementations of type class derivation that you can try, like Magnolia, and there are others. But I have used Magnolia and I have seen some good results, especially with deriving Scala check arbitrary instances. And that's it for me. So, any questions?